Okay, today's topic. I changed the course calendar a little bit because last time I saw that you are pretty good in the basics of C#. So I decided that the topic of pattern matching is something that we don't need to discuss together in school. I think this is too simple for you. You are good enough, you are well equipped, your base knowledge is really good. And I will give you in the next few weeks, one of the homeworks will be to watch one of my existing videos about pattern matching. So you will learn about pattern matching, but probably you just take a look at the video, you understand it, and that's all. So I decided to change the course calendar a little bit and focus today's lesson on asynchronous programming. Let me describe what the whole goal of this stuff is for me. We are working towards entity framework, accessing databases using object relational mappers. And when it comes to entity framework, it's really important to understand two base technologies. One of them is Link. We will do that next week, or we will start that next week. It will be a longer journey because Link is a pretty complex and powerful matter. And the second thing is asynchronous programming. Those base technologies you have to master in order to get started with entity framework. And my experience is that both base technologies are not a given in a fourth class here in the school or in HTLs in general. So therefore, I would like to focus today's lesson on asynchronous programming, okay? Good. We will do some theory. I will do a little bit of drawing on the blackboard, conceptual drawing, so that you understand what asynchronous programming is and why it's important. And then we will spend approximately 2 hours just writing code. Writing simple code with which I can demonstrate how you work in C# with asynchronous programming, especially when accessing the network and when accessing files and databases. Good? Fair? Let's do that. Let's first do a little bit of conceptual drawing. Imagine that you have a computer with a CPU that has, let's say, 2 processors. This is my CPU 1, this is my CPU 2. Now if you start a program in Windows and Linux, whatever, you are starting, in reality, you're starting a process. I think you know that. You know what a process is. I don't need to go into details. If I use any term that you don't know, please interrupt me. Inside of the process, a so-called thread is started. First question to you. What is the difference between a process and a thread? What are characteristic differences between these two things? Yes? Okay, I'm fine with that. If you start 2 of your .NET programs in 2 different processes, one program cannot access the memory of the second process. So we have a kind of process isolation boundary. With threads, it's different. There is something which is called thread local storage. Yes, that's true. But keeping that aside, if you have multiple threads inside of a process, each thread can access all the memory of the entire process. So you can create a list of something. If you have 3 threads, these threads can all access the same list of something, for instance. That's a big difference. Good. I agree. I like that. Next one. How many processes and threads can run on your computer? Are you limited with the number of CPUs? Well, kind of obvious. No, you are not. What's the magic? If you have 20 processes running on a computer with 2 CPUs, who is responsible for running all these 20 processes? Yes, you are.
Operating systems scheduler.
Exactly, the operating system scheduler. You are perfectly right. The processes are distributed across all the CPUs, and if they compete for all the CPUs, okay? So imagine the following situation. You are writing a C# application that does some heavy calculation. Maybe you are doing some rendering, which is CPU bound. Maybe you have a game which doesn't use the GPU, the graphical processing unit, but the CPU. Or maybe you do some mathematical calculation. Think of an insurance company who needs to do some simulation work for insurance programs, for instance. Something like this. If you do that, you typically split up your work into multiple independent units. You write the C# program and you say, okay, in one CPU, I will calculate the upper half of the image, and in the other CPU, I'll calculate the lower part of the image. So you distribute the calculation problem into multiple parts and you run them in parallel. That's the point. So what we have for a certain amount of time here in the CPU 1 running a certain thread, let's call it the thread 1, and at the same time you have on the CPU 2 running another thread, which is called the thread 2 in this case, for instance. And at the end, you are maybe getting the resulting data, you are transferring it here, and here you do the final processing, maybe putting these images together, or whatever calculation you do. Understand? This is called parallel programming. Parallel programming means that you have some CPU-bound stuff which you would like to do really in parallel. At the same point in time, multiple calculations are going on in your CPU. And modern CPUs, even your phones, they have a lot of these CPUs, and therefore a lot of things can happen at the same time. But the point is, if you do parallel programming in C#, you have multiple threads, and these threads are executed on your CPU. Understand? This is not our core focus today. You have to have a clear picture in your mind that there is a huge distinction between parallel programming and asynchronous programming. For parallel programming, you need multiple CPU cores. For async programming, you do not need multiple CPU cores. Let's discuss asynchronous programming. Parallel programming is difficult. It's a complex matter. And we will not touch it in this course, or at least touch it only a little bit. We'll see. Good. Now, let's simulate a computer which only has a single core. Do you think that in practice this is relevant? Do you think that as a developer, as a professional developer nowadays, you have to deal with computers that only have a single core?
I think there are some microcontrollers that are single core.
Okay, microcontrollers, you mean IoT stuff, things like that? Okay, I can tell you, all of you, you will have to deal a lot with computers who have a single core. Even if you do really hard business stuff, if you do web development in large cloud data centers, many, if not most of the computers have a single core. You know why? Because they use virtual machines. And they only dedicate a single core to a single virtual machine. And from your point of view, you have a single core. But of course, the machine in the background has many cores, dozens of cores. In, for instance, Microsoft Azure, the biggest machines have hundreds of cores. So they can run hundreds of virtual machines at the same time, on the same box. But from the point of view of a single virtual machine, you only have a single core. That's not the exception. That's in many cases the rule. Of course, you have many, many, many of those small machines. So you do parallel programming, but you do it in a cluster, in a server farm. But from the point of view of a single computer, of a single program, you often have to deal with a single core. Good. Question?
That doesn't have the single core multi-threading, so it isn't single core anymore?
Not in these virtual machines. They are really single core. You only have a single core. You can only do a single calculation at one point in time. Yeah? It could happen that they have hyperthreading, but it's below your virtual machine. You don't see that. Okay. Question?
I also think server CPUs usually don't have hyperthreading anyways.
It depends, yes. Okay, thank you for this comment. Yeah, thank you for this comment, yeah. Good. So this is our CPU. Now let's discuss async programming. Imagine the following. We are implementing a UI application, maybe in WPF or WinForms or something like this, okay? So if we start a certain program here, let's say this is our UI, we are not on the server side yet. We will discuss the server side in a second. Now we are on the desktop, a simple Windows machine with simulated one core, okay? This is maybe the startup of our WPF app. It draws the main window on the screen. Maybe it starts, I don't know, rendering a beautiful cat image or whatever you want to do. It's just a UI, and at one point in time here, this application is idle. It's waiting for the user to do something, okay? Maybe at one point in time we have a mouse. The user moves the mouse, and when the user moves the mouse, the app becomes active again, handles the mouse move or the keyboard input or whatever the user does, and then it's getting idle again. So at one point in time, maybe here, your application decides that it would like to go to the disk, maybe to a database. Could also be a network application, so you want to call a network service, something like this, and you discuss that you do exactly that. So what you do here is you are running a little bit of code, and this code is doing a database query, or reading a file, or accessing the network. I don't care. Let's stick with the database programming. You did, I think, Oracle, right? Last year? I think so. Imagine that you're running complex query against an Oracle database at that point in time, okay? Now this query here will take a certain amount of time. Okay, let's say this query will be processed in the database in that amount of time. And now we are talking async programming. If you do not do async programming, your thread here will actively wait. It will block the CPU. It will not be busy. It will not do a calculation, but it will simply sit there, and if you compare it with an alarm clock, it sits and stares at the clock and does nothing until the time has elapsed. It sits here doing nothing until the database will return the result of the query. And now in that area here, we have a big problem. In that area, we are blocking the CPU. But we have the user interface, which is also a thread. And therefore, the application does not react on mouse moves, for instance. The application is frozen for the entire time. So that is not a good idea. We shouldn't do that. If we don't do async programming, that will result in very bad user experience. Same is true for the server. We will discuss the server in a second, okay? So this is not a good idea what we did here. What else can we do? Well, we can run a little bit of code here, only a tiny bit of code, which issues the database query. And now something interesting happens. Now we are doing async programming, async processing. That means that we let the database do its job in the background. Something else is busy, not the CPU. The disk subsystem is busy, the Oracle database is busy, the network is busy, but from the point of view of the CPU, we are free. It's no longer necessary to block the CPU core. It's like an alarm clock. We do not watch the clock until time has elapsed. We just set an alarm timer, and then we can do something else. And when the time has elapsed, we are going to be informed actively. So at one point in time, the Oracle database will tell us that it is finished, and that will trigger another piece of asynchronous code where we can do the processing of the results of the database. Maybe we render them on the UI. Maybe we display a nice chart of the data on the UI. And now the important thing is that here, our CPU, our UI thread is free. Understand what I mean? We only have a single core. We cannot do parallel calculations. But if we do tasks which are not CPU bound, we can do them in parallel because of asynchronous programming. They will not limit the use of the CPU. Understand what I mean? That's super important. Of course, in practice, you sometimes use parallel programming, sometimes use asynchronous programming. You can't do both in C#. C# is really, really powerful when it comes to parallel programming. Can you remember a programming language that you have learned about, which does, if you don't apply dirty tricks, which does not support parallel programming at all, but is great in asynchronous programming? JavaScript. Exactly. JavaScript is single core, single thread. If you don't apply dirty tricks, JavaScript will always run on a single thread, full stop. But JavaScript is one of the best languages when it comes to async programming. So C# is a little bit different. C# supports both parallel and asynchronous programming. Questions so far, or is that clear? So that was a UI, an interactive UI. Now let's get rid of this stuff and think about how it works on the server. Let's talk about the server. So now we have a server, let's say, with two CPUs. CPU 1, CPU 2. Here we have a client computer. In my case, it's a laptop, but it can also be a phone, whatever. Anything that has a connection via HTTP. Anything that has a connection via HTTP to our web server. So we are running a web server here on our computer. The web server currently doesn't have any requests, so it's completely idle. Maybe at the beginning, the web server uses a little bit of time for starting up the web server, setting up any kind of network listeners, whatever it does, and then it's idle. Nothing happens. My question is, what happens if the user sends us an HTTP request? HTTP. I don't know. Let's say HTTP GET. I would like to see the awesome cat video. So it does an HTTP GET for any kind of video, okay? What happens? What happens in the web server? Do we have any idea? Yeah?
The server looks for whatever you asked.
Who is the server? The server is a process. Does the server run multiple threads? Or is the server a single process, a single thread?
It's a single process.
Single process. Maybe it can run multiple processes, but let's make it simple. Let's make a simple thought experiment. Let's say you are writing a C# application which has the web server built in, which is typical nowadays. So therefore you are running a single process. And what about threads?
It can have multiple threads.
How many?
How many it can take?
No, that's not true. What happens in modern web servers, at least in C# that's the case, these web servers, they have a pool of threads. That's the so-called thread pool. And by default, I hope that's still the case, at least in the past it was the case, and I'm pretty sure it is still the case. By default, the number of threads in the thread pool are equal to the number of CPU cores. So what it does here at the beginning, when it starts the application, it starts a number of threads in the thread pool. Why doesn't it start 1,000 threads? What do you think? It could start 1,000 threads. Why only 2?
Threads have a lot of overhead.
Yes.
So it takes up a lot of memory.
It takes a lot of memory, and it takes time to start threads. Threads are pretty heavy weight. Every thread uses a pretty decent amount of memory. We are talking in the megabytes here, not just a few kilobytes or bytes. We are talking about megabytes. So creating thousands or tens of thousands of threads, it's really a problem. If you start on a typical .NET web server, 5,000, 10,000 threads, it really depends whether you can start them, because this thread pool has a limit. This thread pool is configurable, but there is a limit to what a machine can handle. So the thread pool should not and cannot grow indefinitely. Typically, you try to keep the thread pool small, not too small. It can outgrow the number of CPUs over time, but typically you try to keep the number of threads small in order to keep your web server efficient. Otherwise, you have to put in a lot of memory. Okay, good. So in this case, we have 2 threads. Each HTTP request is assigned an idle thread in the thread pool. So when an HTTP request comes in, a thread, maybe this one, is currently free. Thread 1 is assigned, let's write it here, with the HTTP request. Okay? So this is our thread 1. It's currently running on CPU 2, and it was taken from the thread pool. You see, it is no longer in the pool. It's no longer free, and it's now dedicated to this HTTP GET request. Now this HTTP GET request does a little bit of processing. It's parsing the incoming request, and now it finds out that it needs to get the funny cat video from disk. And now I think you get the idea, because if we draw the disk here, and let's say reading the cat video will take a little while. If we don't do async programming, then our thread will be blocked for quite a long time. And at the end, we are sending a result back to our client. The problem is that we do not just have one client. We have multiple clients. So if we draw here, maybe here, another client, this time it will be a phone, and this phone will send another HTTP request. Okay, we have a second thread. So we can do this one, we can do this one, something like this. It will also access our beautiful database. It will take a while, and it can send back an HTTP response to our client on the left-hand side. But now we have a problem. What if we have a third client, and a fourth, and a fifth? What if we have hundreds of HTTP requests coming in because our cat video is so hilarious that everybody wants to see it? Then we have a problem. Because what the system will do in the background, it will create, once the threads are gone, it will create additional threads, T3, T4, T5. It will create additional threads and try to schedule those threads on the CPUs. But we only have limited CPUs. You get the idea? So these threads, they keep waiting and waiting and waiting. The CPUs get overloaded. They are idle. They're not doing anything useful in that time. These threads, they are just blocking the CPU. They are not giving it away. The operating system will recognize that these threads are doing nothing. Therefore, it will change its scheduler algorithm, and it will create, as I said, more and more and more and more and more threads. But that's not good, because every thread that the operating system creates uses a lot of resources. Understand what I mean? That's not a good idea. Classically, .NET was known to be a very inefficient web server. You know why? Because of us, .NET developers. Because we always programmed in .NET, classically, synchronous, not asynchronous. We programmed like that. The JavaScript, the Node.js guys, they only had a single thread. They had to do asynchronous processing. So Node.js was way more efficient when it comes to web servers. Understand what I mean? That's a problem. So we have to change the way of programming. We have to change our approach to asynchronous programming, even on the server. So this here is our first CPU. This is our second CPU. And HTTP GET comes in. This is our thread 1. This is our thread 2. So here we have a thread processing the incoming HTTP GET. Here we have our nice little database. And now comes the important part. We are issuing the I/O operation on the database or on the file system or whatever we do. And then we hand back the thread 1. So this is thread 1. It's only locked for a very small time. And once we are done here, the thread gets back to the thread pool. So when the second here, this one, is issuing the request here, it can go again to thread 1 if it wants. So again, we are doing a little bit of processing from the incoming request, and we are accessing the database. Get the idea? So this is something like this. Then the result of the first database query, of this one, this is one, this is the second database query. Now a result comes back here, which belongs to this HTTP request. So we are processing, this is number 3, we are processing the result of the first HTTP request, and we can send back the result to this one. And then the second I/O operation comes back, and we can process here the second I/O operation and send back the result to the second client. And if you take a look now, we only need a single thread, and we can process multiple HTTP requests at the same time. We are not doing parallel programming here. We are doing asynchronous programming here. And the important thing is that asynchronous programming is always used when you do any kind of non-CPU bound work. So if you access a database, a file server, a network, whatever. And if you program like that, your web servers will really be efficient, and they will scale very well. They can handle much more requests than if you do locked programming, not asynchronous programming, locking threads, things like that. You have a question? The parallel programming comes in automatically when it comes to web server programming, because you don't care. You as a developer, you don't do parallel programming. The web server is distributing all the load coming in automatically by using the threads and assigning the threads dynamically to CPUs. So from the point of view of a web server developer, you do not need to program in parallel explicitly, because every HTTP request is scheduled automatically. Parallel programming is really typically used if you have to artificially break a larger problem into multiple pieces and let the CPUs work on these pieces independently. So whenever you do some heavy processing, calculation stuff, then you do parallel programming. But in web server development, and this is primarily what we are focusing here in this course, you don't need to do parallel programming on your own. It's done by the web server. Okay. Not with Node.js. Node.js is different. I told you, JavaScript, single-threaded, not multi-threaded. This is the reason why in the cloud, so many web servers have a single thread. Because if you need more threads, you just spin up additional servers. Do you already know Docker? Yeah, you know Docker? Yes, no, maybe? Not really. Do you have an idea what Docker is? Kind of lightweight virtual machine. The beauty of Docker is that you can very quickly spin up new Docker containers like a virtual machine. So therefore, if you have a web server that is handling a certain amount of load in the cloud, for instance, and you get more clients coming in watching your cat video, you can, like that, spin up additional machines, Docker containers. More and more and more and more. So you are not just using parallel programming on a single machine, but you are spinning up machines. Just like that, you are creating another 1, 2, 3, 10, 20, 100 web servers, and they will handle the load. And then when the load goes down, you throw away the machines. That's a question of milliseconds. That's the beauty of cloud computing. You scale automatically. From the point of view of a single server, there is no multi-threading. But from an overall view, there is multi-threading because you have multiple servers. Okay, got it? Got the difference between parallel programming and async programming? Very nice. I just now hear the clock, so we nailed it from a point of view of time management. That's very nice. That was the theory part, okay? In the next lesson, we are switching gears, going to Visual Studio, and I will show you how to use asynchronous programming in C#, okay? Thank you, 5 minutes break.